In this video, we'll be understanding the working principle of a three-phase induction motor, its advantages, and other concepts or applications related to it. So I'm Mohan BS, working as assistant professor in Department of EEE, SJBIT. So in the diagram, as you can see here in the circuit diagram, so we have three phases represented by one color, three different colors. So these are three different phases which are given to the stator, and there are two types of rotors which we'll be seeing shortly. So one type is called as squirrel cage and the other is called as phase wound rotor. So this is the basic construction part of a three-phase induction motor. So three-phase induction motor is an electromechanical energy conversion device which converts three-phase electrical input to mechanical output. So as said, these are the three inputs, namely R, Y and B. So to the rotor we'll have mechanical shaft which is connected and will take the required output. Three-phase induction motor consists of two main parts as discussed. One is stator and rotor. The stator carries three-phase stator windings respectively. The stator windings is supplied from a three-phase supply. The rotor carries a short-circuited winding called as rotor winding, and that type is called as squirrel cage rotors. The winding drives its voltage and power from the stator windings through electromagnetic induction. So you can see that there is no physical connection between your stator parts, these are your stator parts, and your rotor. So there is no physical connection between them. Then how is the voltage induced? How is the voltage supplied to the stator? How does it rotate? So these concepts we'll study under the working principle. So as it's been clearly told, the voltage and power from the stator winding is being supplied through electromagnetic induction. Now let's see the advantages of three-phase induction motor. It is simple and rigid construction. This requires less maintenance, high efficiency and good power factor. It is less expensive. It has self-starting torque. So when we study single-phase motors, you'll understand the difference between self-starting torque. So let's see the working principle of three-phase induction motor. So as told, the stator is being supplied by three-phase inputs, namely RYB supply, and we have a rotor. We have two types of rotors. One is called a squirrel cage rotor, and that is called as phase wound or slip ring rotor. So we'll discuss much more in detail in upcoming slides or classes with respect to types of rotors. Right. So now, if we have a small air gap, so between rotor and stator, the air gap is too small. Now, as we give supply, so we have three different fluxes which are rotating, namely R, Y and B. So the color indicates the respective colors. This is your R phase, this is your Y phase, and this is your blue phase. So there are three different fluxes which are rotating, but at any point of time we'll have one resultant flux or stator flux, which is also called as rotating magnetic field. So I repeat, so we have three different fluxes, R, Y and B, but at any instant we'll have one resultant flux or stator flux, which is also called as rotating magnetic field, which rotates in the air gap between stator and rotor. So change of flux links the rotor conductors. Right, what happens? So when the change of flux links the conductor, what do we get? We get induced EMF in the rotor. Right? So when we have change of flux which are there, which links the conductor, we get induced EMF. And now assuming that the conductor is being short circuited, we'll have current flowing through the conductors. And because of these current, we'll have one more flux which is called as rotor fluxes. I repeat, so these are your stator flux which is changing, links the rotor conductors, we get induced EMF. Now the rotor conductors are being short circuited. So when we see, when we go for the construction of rotors, you'll understand. So it's like a closed circuit, like now for example, if this is your rotor, so you can see, so these circles which I have drawn here, these are called as end ring. These are called as end rings, where the rotor conductors are being short circuited, thus providing the closed path. Now because of this, what happens, the voltage that is induced across the rotor conductors, as the current flows through the conductors, it produces its own magnetic field. Now this magnetic field is called as rotor flux. Now this rotor flux, the interaction between these two, that is the interaction between a rotating magnetic field and the rotor flux, the rotor will rotate in the same direction of RMF. I repeat, the rotor flux also rotates, trying to catch the speed of rotating magnetic field or stator flux or resultant flux. Now because of that, the rotor will also rotate in the same direction of RMF. But you can observe that there is a difference between the rotor speed and RMF. If both are same, there is no relative difference between them. Thus, the machine will come to standstill. I repeat, when the rotor speed and the stator flux or resultant flux or rotating magnetic field, if they are same, there is no relative difference between them. So there is no change of flux linkage. Thus what will happen? The machine will come to standstill. So there should be the difference. There should be some difference between the rotor speed and the rotating magnetic field. Only then the machine will continuously rotate. Right. So this is the working principle of the three-phase induction motor. And the rotor rotates at a speed known as synchronous speed, which is given by formula 120 F by P, where 120 is a constant, F is a frequency, and P is nothing but number of poles. So number of poles in respect to how many, with respect to your north and south poles in your stator winding. Now why is this called synchronous speed? So NS, what is NS? NS is actually synchronized with F. So when we purchase a machine, the number of poles are defined. So I can say P is constant, 120 is also constant. So thus I can say NS is directly proportional to F. Right? So that means if I increase the frequency, my speed will also increase. If I decrease my frequency, input frequency, my NS, that is rotating speed, or the rotor speed will also decrease. So you can see the electrical quantity is synchronized to your mechanical rotation. Okay, so this is what I am putting in this direction for induction motor. That is, your electrical input is synchronized for your mechanical output. This is also true for your generators. That is, your mechanical input is synchronized for your electrical output. That is, your mechanical rotation is synchronized for your electrical frequency. So as of now, let us not concentrate on this. Let us concentrate on the upper part. So as I change the frequency, my speed also changes. So this is how how the electric car works. So the accelerator is nothing but a frequency knob. So as we change the frequency, as we increase and decrease the frequency, the speed of electric car also increase or decrease, because they are using three-phase induction motors. So this is the biggest application of the current era with respect to three-phase induction motor in your EV vehicles. So again, an example to understand the difference between rotating magnetic field and your NS and stator rotor flux. Now you can see here, assuming that this is being, I just googled it, so assuming that this is a carrot. So what happens here? So when we show a carrot to a donkey, it tries to catch this, and in that way this tries to move. Now when will this stop? It will stop as it eats the carrot. That is, assuming that this is NS and this is the rotor speed. So rotor speed will try to catch NS. Once it catches NS, the donkey will stop. That is, your rotor will stop rotating. Just an analogy to understand how can we remember the concept that NR should always be less than NS. So thank you for watching the video. So please do subscribe the channel to upgrade your knowledge.